There are about 6 types of simple machines. They are inclined plane, screw, wedge, wheel and axle, pulley and levers. Let us learn about each one of them. Have you ever climbed a steep slope? Isn't it difficult to climb a steep slope as compared to a gradual slope? Yes, it's easier to climb a gradual slope. Thus we can say a gradual slope makes our work easier. Such a gradually sloping surface is called an inclined plane, and it helps us lift heavy objects. Let's see some examples where inclined planes are used. When the workers have to load or unload the truck, they use a plank of wood as an inclined plane. Even in the hospitals, ramps are made to make it easier to move the wheelchairs. The steps which you use to climb up are also an inclined plane. Imagine climbing those heights without the steps. Even the slide in the park is an inclined plane. The next simple machine is a screw. We all have seen screws on revolving stools, chairs, and ear studs. The screws help hold the things tightly. But did you know that a screw is also an inclined plane? Let's see how. Have you seen the roads on the mountains? They are built in 2 ways. Steep slope, where walking is difficult because it needs a lot of effort, and a gradual slope, where walking is easy as it is similar to an inclined plane. Most hills have winding roads with gradual slopes. Don't you think that a metal screw also looks like a winding road on a hill? The groove gradually rises from one end to the other. In fact, every turn of the groove is also an inclined plane, which helps you to move it with less effort. This helps the screw to get into the wood and hold it tight. So we can say a screw is an inclined plane, but in the form of spirals. Let us perform an activity to prove that a screw is an inclined plane. For this activity, you will need a piece of paper, a pencil, a pair of scissors and a crayon. Cut a right-angled triangle out of the paper. Color the edge that is opposite to the right angle. Take a pencil and wrap the edge around it. Now, compare the pencil with the screw. The colored edge forms the edge of the screw, which is inclined. Let's look at some more examples of screws. Jar lid, bolt, and drill are some examples of screws. We all know both screws and nails are used to join things. If we use a nail and a screw of the same length, which will hold the things better? When we join things with a nail, they are held to the distance equivalent to the nail's length. But in the case of a screw, the things are joined along the spirals, which is a longer distance as compared to a nail. This makes it very difficult to take them apart. Hence, we can say that screws hold better than nails. Some screws are quite big, known as screw jacks. Heavy objects, such as cars, are lifted using screw jacks. Next, simple machine in a wedge. To understand a wedge, look at a blade of the axe. You will find that it consists of two inclined planes, which are joined and forms the sharp edge. This is called a wedge. The wedge is used to cut or split an object. Some examples of wedges are axe, knife, fork, chisel, and needle. Wedges are probably the oldest machines used by humans. At times, wedges are also used to keep a saw cut open. We already know that pushing objects on wheels is easier than lifting the load. But it is interesting to note that a wheel alone is not a machine. When a rod known as an axle is attached to the wheel, then it forms a machine. In a wheel-axle arrangement, the wheel and axle move together and require less effort. Wheel helps in moving the heavier objects and can even be used to change the direction of the force. Wheel and axle arrangements are found in all vehicles and their steering wheels, knobs of the door, sewing machine, blades of the mixer, and washing machine, etc. Did you know that even the screwdriver and the knob of the tap are examples of wheel and axle? Some wheels have teeth on them. They are called gears. Pulleys are most commonly used to draw out water from wells. A pulley is just like a wheel, but with a groove around the outer edge. The rope runs through this groove. A pulley changes the direction of force. For example, while drawing water from the well, when the rope is pulled downwards, the pot rises upward. Isn't that interesting? A pulley can be of two types: fixed pulley or movable pulley. In fixed pulley, a single pulley is used, such as the one used for drawing water from the well, or the small pulley used on a flag post to hoist the flag. Have you ever noticed this little pulley? In a movable pulley, a number of pulleys are used. For example, you can see many pulleys in a crane. They help the crane lift or lower heavy objects very easily and shift to other places. Have you ever tried to open the lid of a container using a spoon or a screwdriver? This spoon or screwdriver acts as a simple machine called lever. Notice that when you put a downward force on the screwdriver or the spoon, the lid opens upwards. Thus, the screwdriver or spoon acts like a simple machine, changing the direction of the force applied. Let's take another example to understand the working of levers better. Sometimes we use a rod or bar to lift a heavy load like a rock. A small stone is kept under this rod, which is quite close to the heavy rock. When the person applies a downward force on the other end of the rock lifts. In this case, the rod used to lift the rock is the lever. The weight lifted, that is the rock, is called the load. The small rock under the rod is the first fixed point around which the rod can be moved. This pivot point, or the point of support, is called the fulcrum. The fulcrum helps increase the intensity of the force and even change the direction of the force. The force applied is called the effort. We can classify levers according to the position of the fulcrum, load, and effort, as first-class lever, second-class lever, and third-class lever. Let's learn about all these one by one. In the example of opening the tin and lifting the rock using the lever, the fulcrum was between the load and effort. Such levers that have the fulcrum is in between the load and effort are called first-class levers. Some other examples of first-class lever are a seesaw. You must have played on it. Scissors, hammers, physical balance, pliers, crowbar, and handle of a hand pump. It is interesting to note that we require less effort when fulcrum is near to load. To understand this, let us perform an activity. For this, you will need a ruler, a pencil, and some coins. Keep the coins on a table. Take a ruler and place the pencil beneath the ruler and try to lift those coins. You will notice that when the pencil is placed near your hand, it takes more effort to lift the coin. And when you place the pencil near the coin, you are able to lift the coins easily as it requires less effort. Thus, it proves that less effort is required to lift a load when the fulcrum is closer to the load. To understand second-class levers, take the example of a bottle opener. When you try to open a bottle with a bottle opener, the bottle acts as the load. The fulcrum is at one end of the opener, and the force applied by our hand is the effort. So when you pull the handle of the opener upwards, the can opens. Notice that in this case, the load is in between the fulcrum and the effort. Such levers where the load is in between the fulcrum and the effort are called second-class levers. Some examples of second-class levers are wheelbarrow and nutcracker. In the third-class levers, the effort is in the center, that is, between load and the fulcrum. In the third-class lever, since the fulcrum is far away from the load, the effort used to lift the load is always greater than the load. Hence, they are not very helpful. Some common examples of third-class levers are tongs, a broom, tweezers, a baseball bat, and a shovel. Did you know that the pyramids of Egypt are made up of large blocks of stones? But it is interesting to note that these huge stones are lifted, transported, and placed in a position with the help of simple machines like inclined planes, lever, pulleys, and wheels.